Okay, good afternoon, everybody. How are you going? Is that right? Is that how you say it? Thank you for coming. I hope lunch was awesome. I haven't had any. I'm going to have it after this, but I hope it was great. So thank you for coming to this session. My name is Lok Hui. You can just call me Lok. An easier way is just to say joke, but with an L. I would prefer to be Loki, but then, a god of mischief is hard to follow. Anyway, so I've been in Microsoft for 10 years. Most recently, before joining the robotics team, I've worked in Windows Phone and Windows Mobile for about 4.5 years. So in our team, we're only a small organization. We are sort of a sister division to the Microsoft Research. It's called Microsoft Robotics. And what we do, we have about 25 people in the team today. And what we do is we are actually trying to develop new software technologies and also proof of concepts to sort of tell robotics research developers, what kind of robots can you make? What kind of robots, where is the avenue we should move towards in order to reach the end goal? And the end goal has been laid out by Bill Gates many years ago when he said that a robot in every home. How many of you have remembered that? Okay, a PC in every home, a phone in every hand, right? And then a robot in every home as well. Well, I don't know if we'll get there or not within my lifetime, but we're certainly going to try. So we do not create products. We do have a toolkit that we publish called the Robotics Developer Studio. We're in the 4th version of that tool today. It's available for free on Microsoft.com/robotics if you're interested. But today's talk is all about this guy. This is Roborazzi. Say hello. Well, obviously he's not going to say hello back to you. But how many of you encountered Roborazzi in the halls the past few days? Wow. So I've got all your photos then on Flickr. So what it does is it's a party photographer. I'll talk more about it. I talk more about when we design this robot, although the title says human-centric robot, the talk is not about building a humanoid robot. That is a completely different topic, which, after this discussion, you will understand why we're not there yet. But human-centric robot basically means a robot that lives and interacts with humans. Okay? So this talk is going to be about that. Now, all of us want robots, right? Do all of you want robots? Do you have any at home? You do? What kind of robots? A Roomba. Exactly. Now, anybody else have any robots at home? What kind of robots would you want at home? Just R2-D2? I've got that. No, I'm just kidding. But, what else? What kind of robots? We've seen it in the movies, right? We've lived it. We've experienced it. We've dreamt about having robots at home. We've seen it in science fiction movies, but nobody has that kind of robot at home today. Why? Why isn't there any robots like that? I mean, robots has been in science fiction since, let me see, the actual term robot was first coined by Karel Čapek in his play in the 1920s, Rossum's Universal Robots. That's the name of the play. And from that moment on, the term robot was used to describe automatons, or an autonomous device, mechanical device. But in his play, the robots are, technically androids, not robots. So since 1920s, but where are these robots? Still. So hopefully in my discussion, I'll tell you why we don't have robots at home today. Having been involved in the business for 2.5 years, I've seen, the apex of the research and development for robots, and we've also seen how it is used to teach the concepts for programming as well. So let's have some definition first. What is a personal robot? Let's talk about personal robots. There are many different types of robots in the industry. Industrial robots, military robots, fixed robots, personal robots, household robots, service robots, and so forth. Let's talk about personal robot. Personal robot is a device that can autonomously move all or parts of itself through a home and do something useful. Okay? So let's hone in on 4 words. One is device. A robot is essentially a mechanical device. Okay? It has to be a mechanical device. Either it's a PC running some software, or it could be a complete, just a mechanical device that moves around. Now, there are advances in biomechanical engineering that maybe one day we will have a robot that's all biomechanical. But, instead of just helping to increase the crop yields, somebody might take that research and build a robot. But let's not talk about that. That's actually a pretty interesting topic. Let's talk about a device, a mechanical device. Now, the idea here is the mechanical device needs to be able to move Otherwise, it's not a robot. Okay? If you have a mechanical device that is stationary and does not move, there are no arms. When I say move, doesn't mean that it has to move along different locations. Move, it could be an arm, a stationary arm that moves as parts of itself. If it does not move, then it's just a machine or a personal computer. Okay? So a device that must move, not only move, but move autonomously. Why is that important? If the device moves under a human control, then that's called remote control. Right? Teleoperated. It's not autonomous. Hence, there's no perceived intelligence behind a remote control device. You can't call it a robot. Right? Correct? Would you agree? Okay? Correct. So things like remote control, you see a lot of hobbyists build UAVs, at home and say, this is my robot. Robot moves around in a home, but actually it's remote control. How can you call it a robot? That's no intelligence at all, okay? And the last piece is do something useful, which is, I've talked to so many hobbyists and so many robot developers, and half the time I talk to them, they will say, wow, you know what, I built the robot from ground up, I bought the parts from Servo City, I bought the parts from an online website, I put it together, and now it moves. How does it move? Oh, there, look, I'll show you, I'll push it, I'll make it move. But then what else can it do? Nothing, just moves. What? What do you mean it just moves? It is not useful. Well, maybe from an expectation perspective, if all I need the robot to do is move, then yes, it's useful. All right, great, fine, right? But if a device that autonomously moves and doesn't do anything useful, then it doesn't make sense to have, okay? So a personal robot is something that is a device that autonomously is able to move around or does something useful for you. Some can argue, especially in the elderly care scenarios, a companion robot. It could be just a robot that follows you wherever you go and says nice things to you. You look beautiful today. Oh, your hair is sparkling and so forth. To a certain extent, that is useful, right? Would you say so? So that's the definition of a personal robot. Now, do you know that there are so many of these robots now already being used? In this case, the Mars rover, although there's a new one called Curiosity, it is a robot. It is a mechanical device. It's able to autonomously move, right? Obviously, by having remote operators nudge it and say, I want you to do this, I want you to do that, and it will autonomously move and navigate on its own. And it does something useful, of course, it does. So that we've been using that for decades already, okay? Industrial robots are common. They're commonplace everywhere. I think last year, if I'm not mistaken, there have been over 300,000 robotic arms sold in the world to manufacturers and factories worldwide. That's a lot. That's like $1 billion business, okay, if you're in industrial robotics. But then you have a whole slew of problems to think about industrial robots. But it's being used for, again, decades. And military is also big on robots. You've seen UAVs, you've seen bomb disposal robots that will navigate and prod and poke IEDs, and then when it blows up, you don't lose a person, you just lose a couple of $1,000. Okay? So those are also useful devices. But at home, right, somebody over here has one. There we go. Now, do you realize in a commercial robotics or consumer robotics field, there are only 2 successful implementations of what we call robots today. One is the vacuum cleaner. Actually, 3. The second one is a lawn mower now. There's a new one, which is pretty cool. And the third one are basically toys. Playos, Lego, Mindstorm, NXTs. They're all just toys. They don't do anything useful except to entertain your kids. Well, in a way, that's pretty useful too. Right? Take this so that I can play my games instead. So, so there are only 3. There are no other commercial success stories for robots. I wonder why. Why is it that all the technology has been used for decades? In the military, industrial, in space exploration, but none of it has been brought down to a consumer level. I have 3 reasons for you. Okay? Let's talk about the 3 reasons. The first reason is the environment we live in, your home, your office, this place, this theater, this convention center, is discriminating against robots. Why? Because look at the door, for instance. Why does a door have a handle? It is for us to use our hands to open the door. And you can also lock the door, for instance. Now, if you were to design an environment for a robot to live in, do you think you put a handle on the door? You don't need it. Why do you need that? Why can't the robot have an RFID, come near the door, and the door opens? Or why can't you have a robot that has a screw arm like R2-D2, and the knob on the door is just a hole, you just put the screw in, turn, and open the door? Actually, why have doors? Right? So the concept here is the more useful or the more convenient we make our homes, the more difficult it is to create a robot that lives in it, which is very funny. So as we progress as human beings, right, the more convenient our homes are to us, the more difficult it is for somebody to create a robot to live in that home. Seriously, I mean, how many of you live in multi-story homes? Okay, you have staircases, right? Now, the staircase is like the ultimate difficult thing for a robot to transcend. For a human being, it might be simple, just go up, walk, use your legs and walk up. But for a robot, oh my gosh, how many things do you need to consider when you make a robot to go upstairs? The placement, the motors, the servos that you need to turn, the balance of the robot in real time. What if something pushes, what if you need to carry something up on the staircase? It's so difficult. It is achievable in research. Now you have walking robots, you have running robots, but in a very controlled environment. Not only that, you need to think about the security of robots, living with a robot. Okay? If Microsoft were to create a robot and sell it to you, do you think there would be a legal problem that we need to address? What if the robot kills somebody? What if it steps on your foot? What if it destroys your home? Okay, the joke is, what if it blue screens and then the robot flies everywhere, right? Okay, yes, I know. I've heard that joke a million times. Yeah, we worry about that. It's not just for Microsoft technology, any technology. You guys know, you guys are developers, you understand code. There can never be perfect code. It's just how well you can react to environment. So the environment is very discriminating. Now, I'm going to show you a video. Take a look at it.
Can you hear me?
Yes.
ID.
KPC 897504C.
Can you move your head? Your eyes now. Cervical and optical animation checked. Now give me your initialization text.
Hello. I'm a third generation AX400 android. I can look after your house, do the cooking, mind the kids. I organize your appointments. I speak 300 languages, and I am entirely at your disposal as a sexual partner. No need to feed.
Okay, so apart from the last part, the last bit, now you realize that when you hear what she says, she tells you what she can do. She never says anything about doing your laundry or doing your lawn, or she did say cooking, but tedious tasks, what we call blue-collar tasks, is not something that interests us as human beings. We prefer white-collar robots. We prefer robots that can help us do things that we love. Okay? But there's a huge, drastic difference between white-collar tasks and blue-collar tasks. Okay? So let me give you an example of a blue-collar task. How many of you have grandparents that use something like this? This is how they used to do laundry, right? They heat up the water, they wash the clothes, and then they run it through this press. Now, this is actually pretty modern because it's an electrical-powered press. I think my grandma has a hand-cranked one, right, those days. Now, what's really interesting is, if you went back in time and you asked your grandma, if I were to build you a robot that can help you make this process much faster, how would she want it to be? She'll probably tell you, I want a robot to be able to dump the clothes in hot water, carry the whole pot without spilling any of the water, bring it over to this appliance, and run all the clothes and towels through it, and then pick it up. Okay? That's what she will probably ask you to do. But what's interesting is, fast forward a couple of decades into the future, how did we help solve the problem of laundry today? Washing machines, dryers. Now, did you see anywhere in that story where you actually have a robot pick the clothes and push it through the press? No, we've thought about it from a different point of view. We thought about it from a different abstract point. We said that, look, the task is to automate make laundry, cleaning your clothes, not having somebody replicate what you do. How do you know whether that's the most efficient thing to do? We don't know. So what we're saying here is what we actually need is not a robot. It's just automation, mechanical automation. For instance, I do laundry at home. That's like the worst thing to do. Do you guys do laundry? Those of you who do laundry will understand, right? Not just washing and drying, it is the folding that kills you. Okay? Because and the worst thing is my kids will then take out their shirt and it's upside down, and then they just throw it into the washer. When it comes up, you have to flip everything all over again. It is so hard. I wish there was a robot who could help me do that. Or I wish there could be a device. It doesn't necessarily have to be a humanoid and then do laundry like that. Why? There is a research organization in the US. They built a robot called PR2. It's a $500,000 robot with Kinect sensors, laser rangefinders, two 7 degree of freedom arms. And one of the scenarios that they show on a YouTube channel is them folding a towel. Just one towel. 15 minutes to fold one towel. I think my kid, with enough coaxing, can do it in less time than that. But it's a towel, it's square. It's solid color towel, and it's square, and it took them 15 minutes. Now imagine having to program that robot to recognize T-shirts. Not only that, not just T-shirts would be great, but T-shirts, women's dresses, jackets, shirts of different length, different material. How are you going to figure out how to do that? That is actually a pretty difficult task, right? But we want home automation. We want to do that. But that's actually what we need. But what we want is the robots can help us do all the white-collar jobs. And it's really, really hard. We're definitely not there yet. The second point is social unintelligence. As developers, you know, we live in a world of classes, constructs, methods, functions, and so forth. When you have to replicate intelligent behavior, you do it in a variety of ways. The most commonly is case or if-then, a billion if statements, or maybe even write code that is able to learn itself. But I'm not an AI expert, neither are most of the engineers in our team, because AI is still not there yet. We've been talking about artificial intelligence for years, just trying to teach it intelligence. Now try teaching a robot to be socially intelligent. No way that's going to happen. Being able to understand the quirks, the emotions of the person that they're dealing with, the people around them, socially aware, it's going to take years. We are not there yet at all. You know, you need to solve this problem in order to have the robot live at home and to conduct or do white-collar tasks, to live with you, to be your partner. It's hard, okay? So that's why we're not there yet. And the third piece is there's a lack of reference platforms. Now, why is iPhone, why is the iPad, Windows Phone, Android all so popular? Why are there so many apps and capabilities for the device? Why is Windows used in so many different countries, so many different areas? There's a ton of capabilities for it, correct? There are a ton of apps that you've built as software developers that can make that operating system useful, okay? That is because you have a platform to build on top of. Now imagine in the robotics world today, there is no fixed reference platform. There's no robot that says, look, everybody build something for this robot. Today, if you want to get into robotics, the first thing you need to do is build that robot from a hardware perspective. How do you want it to look like? Do I want it to walk? Do I want it to move, drive around? Do I want to put arms? Okay, maybe you will say, all right, I want a robot with two arms. And that guy over there, no, I don't really need arms, I just want it to move, so he just puts wheels. And then the other guy over there might say, all right, I want the robot to fly. And what happened is you spend all the time, 1 or 2 years, building this robot from a hardware perspective. And at the end of the day, it doesn't do anything. It's not a platform that anybody else can build upon. And thus, there is no progress. A lot of kids will tell you, I don't know if some of your kids are into robotics, it's a great way of teaching people about mechanical software engineering, right? Software plus hardware. It's a great way to teach them. And whatever they teach in school, teach you how to build a robot and program the robot to do one task. After that, what do? They move on. There is no commercial viability use of the software to push the industry forward. So there's a lack of a reference platform. And we tried to change it by introducing Eddie. Now, Eddie is a robot that we built together with a company called Parallax. They are based in Rocklin, California, and they built the small sumo bots and a few bots, and they build quadcopters. They even have an octocopter, 8-propeller robot, and they built this. The reason why we needed a reference platform so that we can go out and tell all the developers, hey, if you're thinking about making a useful robot and you want to stretch your imagination and you want to write the code and make the robot do something useful, do it on this platform. Start from here. Don't build the hardware again. Just start from here. And then, if you want to customize it, you want to put an arm on Eddie, fine, put an arm on Eddie. But at least there's a reference platform where you can start from. And we created this one. So the base is a Delrin base. You can see we have that. Roborazzi is built upon the base as well. It's a Delrin base with 2 differential drive motors and 2 caster wheels so that it will balance the robot. We actually have a version of this in the office without the 2 caster wheels. And it's balanced like a Segway. So one of our engineers built the code to balance the robot, which is pretty cool. And we use a laptop as the brain because the laptop is so flexible. Not only that, everybody knows how to use a laptop. Everybody knows how to use the development tools for the laptop, right? Why write some low-level programming environment that forces the developer to learn again the platform? Okay? Start with something simple and useful. And obviously, the laptop runs Windows, right? Okay, you can run anything on it, but in our case, you can run Windows. Actually, it's not that kind of brain. It's actually this brain, in fact. Actually, it's more like this brain. But so let's go with that. And we introduced a device called Kinect. Now, Kinect is amazing. It is an amazing sensor, especially for robotics. You know how useful Kinect is for human-PC interaction, right? You can make Kinect do all kinds of stuff. You can play games using Kinect. But it is even better for robotics. You can do two things practically in robotics. One is navigation. You can replace really, really expensive laser rangefinders, LiDARs that cost $5,000, and you can just buy $150, and it will replicate the same kind of functionality. Right? It's great for robotics. It's cheap as well. The second thing you can do with Kinect is not only have it use Kinect as a navigation, you can also interact with your robot if you want to. So human-robot interaction, speech, because the Kinect is also the eyes and the ears. You can talk to it. There are 2 microphones, so you can actually have directional information. So the robot will know that if you speak on the right-hand side, you can turn the robot around if you want to face the user. So we use Kinect, and we have the Kinect for Windows SDK available that you can use Visual Studio and write to and talk to Kinect. The basic Eddie also comes with ultrasonic ping sensors, which are those 2 that the ears are covered now. It's just the reason why we have sensors or ping sensors, sonar sensors, is so that certain visuals-based sensors cannot look past or cannot see windows or glass. If you use infrared sensors and you go towards a piece of glass, it will think that there's nothing there, right? And it will just knock into it. But whereas a sonar will bounce the signal off the glass. So we have sonar sensors, and then we have the proximity infrared sensors as well, right at the bottom of the base. Now, anybody want to ask why? Anybody knows why the sensors are put at the bottom? At the bottom of the base? Sorry? Closest point to where you want to hit something. Correct. Now, we have a Kinect sensor up there. We can use it to navigate and avoid obstacles. But the Kinect has a limited angle, right? You can't see like 1 feet in front of the disk right here. So we need to have something that's right down at the bottom to be able to detect obstacles. I will describe to you how we solved that problem using Roborazzi. Even better solution. Perfect solution for obstacle detection. And then it's powered by 2 lead-acid batteries. This is fantastic because they have a lot of power and you can ship it. You can ship it anywhere internationally without having to worry about shipping lithium-ion batteries. I personally had this experience. The laptop you see up there has a lithium-ion battery. And when we shipped this robot here, we had to take it out because they don't allow us to ship lithium batteries internationally. Fine, I want to hand carry it. I put it in my luggage, I check it in my plane, I arrive here, 3 days ago. The luggage arrived yesterday. So I didn't have those batteries to use, so I had to use my other laptop and all that mess. But okay, so it's powered by lead-acid batteries, and that's it. So that's how the stock Eddy looks like. Now, if you look at Roborazzi over here, you realize that we don't have the second deck. We removed the second deck, and we raised the profile up higher, about 4 feet, about 3.5 feet. I'll talk about why we do that. So if you're interested, you can go to parallax.com/Eddy. I'm not selling anything, but if you guys want to try, dabble into robotics development, and you want to think about it from the software perspective, try this. Now, we ran a competition called the Robotics at Home competition a year ago, and we had 10 people submit the final projects, and we picked the top 3 winners. The first winner is a robotic smart tripod. How many of you do YouTube videos? You have like a own hobby. You usually have your camera pointed at you yourself, or you have it on a tripod, right? And then if you want to change your angle, you need to move the tripod somewhere else, or get somebody to help you. But imagine if you had a robot that can walk with you, and yes, you can talk to the camera, the robot will move away, keep your distance away from you. When you're doing something, it will focus the camera down on what you're doing. And you can even program it to be a dolly, so you can say, all right, robot, move in a circle around me while I talk. And you have this nice matrix-like effect, right? You can do that as well. So that's a smart tripod. The second prize winner was a healthcare robot. You know the concept where you've fallen and you can't get up, especially an elderly person? You've fallen down, you say, hey, Eddy, help me, I'm fallen down. And then the robot will come and call a call center, and the person can start a Skype call with you and call 911 or 999, whatever that is here. So we have that. And the third piece is a dance teacher. Pretty funny robot. So what it does is, Dance Central, right? On Xbox, you can dance on the game. But here, you can actually project foot placements for you. And then play the music and say, okay, and then teach you how to dance. Teach you how to do the, whatever they call that. The Gangnam style? Okay, let's hope nobody does that. So interesting use of the same base, same reference platform, but customized for specific useful scenario. And that's what we want to try and cultivate. So another example is Darwin Bot. Okay, this is created by our engineer. And Darwin is the name of his dog, which you will see in a preceding video, or the video coming up. And it is a pet companion. You can call in using Skype. You can control the robot remotely if you want to. You can trigger the ball launcher to launch the ball. The pet will pick the ball and bring the ball back. Why? Because when the pet brings the ball back, it can trigger it, and you can drop treats for it. And there's a robotic arm that picks the ball and resets everything again. Okay? So here's the video of what Darwin does.
Darwin, come! Darwin! Good boy, Darwin. Darwin, sit. Good boy. Good boy, Darwin.
At all. It looks more like a small dinosaur. So that's Darwin Bot. He created it because he wanted to be able to play with his pet when he's traveling and so forth. So that's an interesting implementation of the same base, but customized with additional hardware. And you look at it, he's actually using a Windows 7 Slate at that time. But I'm sure he'll upgrade to Windows 8 when it's available. So let's talk about Roborazzi. You guys are here to hear about this, to see how we actually built it. The person that put most of the hardware together and the software is Greg Shirakan. He's one of our principal researchers. I worked with him to build this, and this robot you see here is the third iteration, actually Roborazzi 2+, not just 2. We recently added a tilt mechanism up here for the camera to go up and down. Now, the original intention of us for doing this was we were sat down in a room, and a bunch of us brainstormed. If we had this base, what would you want to make it do? If you had one at home, what would you make it do? So we came out a long list, and we sorted through the list, and we got all the engineers and the VPs and GMs to vote through the list. And there were a few that came top. And one of the concepts was a party photographer. Having a robot move around at home while you're having a party, taking pictures for you. Okay? I don't know if you've seen some of those photo booths. I mean, how many of you have been to a party where they have a photo booth and all kinds of funny fuzzy hats and glasses? And it's actually pretty popular, right? They will just stand in front, they will dominate that thing. So why can't you have one that's mobile, that moves around, takes the pictures for you, not just take the picture for you, upload it to a cloud service that you can come in later in the future and then make a video, and then you can send it to all your friends. Wouldn't that be pretty cool? Okay? So that was the idea, how it all started. And we designed, the first version of it is much lower. It's very short. We had a camera pointing up. It worked well for taking kids' parties, but for adult parties, a little bit too edgy. Especially the women who walk near to the device, that's a little bit too... And, taking pictures from the bottom up is a terrible angle anyway, right? So we decided to bring it up higher. And then what we learned through the process of creating Roborazzi is we learned so many things, not from a technical perspective. I'll tell you, the code to do this is so simple you would not believe. It's so simple. I explained to you how we even do the complex navigation. It is the interaction with people that was the difficult part. We never knew that people were so adaptive. They could make this device do certain things that you never encountered or thought about doing. So then we have to quickly come back and say, okay, let's change the parameters a little bit. Let's add a little bit of code to do some certain things. The reason why we added a tilt mechanism is because the camera has a fixed focal length, fixed zoom. So when you come up to a person, if it's 6 feet away, you would take the whole person, right, depending on zoom level. If you're up close, then you take a picture of your name tag, which we did quite a lot. But so what we did was we decided to detect the height of the person and say, okay, if this person is high, tilt the camera up so that you get better shots. But what's interesting is, if you've seen it go around, we've run this for so many different events. We've taken thousands of photographs. A lot of it are throwaway kind of photographs. Like the back of somebody, the name tag, or the back of the face, or something useless like that. But there are some pictures that are pretty interesting. We won the Maker Faire Editor's Choice Awards for running this robot, not because it was a technical achievement. It was the interaction with the kids and the people in the fair. That was pretty interesting for the Maker Faire guys. So this is one of the photos that we took. Now, what's really interesting is this robot was actually like 10 foot away from this plant. And he decided that the plant is interesting, went near it, took a picture, and then walked and then moved away. And the people that were watching were perplexed. They're like, wow, that's a new Andy Warhol in the making, or something like that. And they were but we never wrote that code. We never told the robot to go and look for plants and took a picture. So all these interesting emergent behaviors will surface. The second one is like this. Some will argue that this is artistic, right? I'm sure if you use Instagram to tint the color a little bit and then put it on a big museum, everybody will go, "Oh, that is amazing." But it's just one of the error photographs that we took. Okay, that's interesting too. But most of the photographs ended up being something like this. It is amazing to see kids play with the robot. They come in front of the robot, they crowd around it, they know how to work it. If you take a camera and you point it at children, they will most likely run away. But having this camera on a robot, everybody was crowding and wanting to get the pictures taken. And what was very interesting for us, was very fulfilling for me personally, was every time it takes a picture of somebody, you will see the smile on their face. Instantly. It happened here as well. I don't know if you guys, probably because you saw the picture of yourself, oh my gosh, that looks like crap. And you smile just for the sake of it, right? Yeah, but it's a great effect, the way it interacts with people. And again, we never wrote any of this code. We never wrote code that says, make that guy smile. There's no such thing, all right? I mean, that's what I'm just trying to tell you. So a lot of photos are like that. So the idea here is we need to think, if you're building a robot, we need to get out the weeds and not think of it as functions and abstracts and classes, but think about it from white-collar type of development rules. What does that mean? The first thing is perfect is not cool. We are all perfectionists, right? I wrote a lot of code in my past, and it nags me every time that I know that there's one function that I could have improved upon, but I just let it go anyway. Right? I know it happens to you. We're all perfectionists. But the problem here is being perfect, especially in a robotics field, can be very, very challenging. If you spend, like for instance, 30% of the photos that Roborazzi takes will be useful. 70% is throwaway work. As engineers, we would think, why can't we program it and make it more accurate? Make it reach up to 90% accuracy so that all the photos will look nice. And to do that, you need to spend a ton of time just trying to make it work, trying to make it perfect. Especially when you're dealing with human beings, there's no such thing as perfection. People are so adaptive, people change, the wants and needs are so different. What's important is being able to know what works and what doesn't, and then just let it fly. Just let it go. You know, there's so many things that I keep telling most of you, I don't know, those of you who I've met in the halls, I tell you, why don't we make an algorithm to detect the face? So that when there's a face and a skeletal structure, you will zoom in on a person and take a picture instead of taking a picture of the person behind. What about zooming? What about changing the ISO? What about changing the f-stops and and all those capabilities just to take that perfect shot? But if you realize half of the time the robot is trying to chase people down, he sees you, you walk away, and he loses the person. The person is not going to stand there for 30 seconds. My wife's a professional photographer, and half the time the subjects have to stand still for a while because you have to compose, get the right color correct, I can't remember what all the terms are. But you stand and get that one shot, okay? For something like this, you can't be that perfect. So we try to deal with the fact that it is a very imperfect world around you. The second piece is sensors rule. You need to have rich sensors in order to do rich behaviors. For instance, without Kinect, it was very hard for anybody or for us to implement person detection. It's actually a very, very difficult science. Using a web camera to detect somebody, how do you know if that somebody is a blob or a dog or what? It's hard. But Kinect enabled skeletal tracking. And all we did was just say, okay, if the skeleton is in this spot, take a picture. So you can imagine 3-4 lines of code to do that, and you're done. Okay? So rich sensors enable rich capabilities. There are a lot of sensors that are available today in the market that are really, really expensive, used in the military industrial robotics scenario. Hopefully, those sensors can come down to a much cheaper rate, cheaper price, so that you can create all kinds of amazing stuff, right? And the third piece is you need to be adaptive. You need to develop a sandbox that you can customize the robot on the fly and detect emergent behaviors, okay? What do you mean by emergent behaviors? Emergent behaviors are things that the robot can do that you never wrote any code for. For instance, if you look at how this robot navigates, it is actually very smooth. If you put a few obstacles, it will move in a very smooth line, detecting obstacles and going around them. Most of the robots you see in a hobbyist scenario will go, oh, there's an obstacle, turn, and then move. Oh no, there's a drop, turn, and then walk like that. It's hardly smooth at all. If you need to write code to make it smooth, you need to go, oh, okay, fine. If there's an obstacle here, I need to create a Bezier curve, and follow that path, and you write all the logic just to make it avoid. How we did our navigation is very simple. We just used a mathematical formula that says, if the distance of the object is this far away, I want you to turn slowly at a different rate. If it's close, I want you to turn faster. Okay? That's pretty simple logic. The next thing we did was, in every aspect, every mechanical aspect of the device, we implemented a smoothing function. So we remember that the variable for speed is 100 when you're moving. If you need to go to 0, it doesn't immediately stop the motor 0. It smooths that number down to 0. That's all we implemented. And the result is the robot will move, it will start turning at a slow rate, and then when you see another obstacle here, it turns at a slow rate, and the result is a very smooth navigation capability that emerged from just writing 3 functions. It has nothing to do with making it go smooth. Making it smooth, well, you did was smoothing function, but everything, even the tilt mechanism, even turning, even detection, everything is all pushed through this filter, the smoothing filter. So how did we find out in the first place? When we did the navigation, we never knew this could happen. And in order to tweak it, you need to create a sandbox. And in our case, the sandbox is just basically variables. Let me see if I can show you. Let me just switch to... so this is the app that we built called Roborazzi, what you're seeing here. Okay? And let me just switch to Kinect here. The big display is the downward-facing Kinect. And the one on the top right is the forward-facing Kinect. So if you look at this piece of hardware, let me just guide you through, okay? So this is the Eddy base. It's a Delrin base with 2 very strong motors that can go very fast, almost as fast as a human can walk, so or trot. And it's powered by a propeller board from Parallax. And all of it is connected to the PC via USB. We have 2 Kinect sensors, one at the bottom that looks in front for skeletal detection, and the top Kinect looking down for obstacle detection. Okay? And then we have a tilt servo with a Canon Rebel T3i camera, and we talk to the camera using USB using the Canon APIs. Everything else, you see here, the scaffolding is our 80/20 beams that we can just bolt on to this and raise the profile up high. And then that's just a Windows 7 PC. So the idea for obstacle detection, in the past, how they did it was they used infrared sensors, they used sonar sensors, and they come up to an obstacle, and he knows there's an obstacle somewhere around here because it's come close to me, I want you to avoid. The problem is if the obstacle is far away, you don't see it yet until you come in to within the range of the infrared sensors. If you want an infrared sensor to see far away, it's actually pretty expensive. Right? And it gets more inaccurate as the further you go. The way we solve it is point the Kinect down, and if you see a change in depth, okay, mark it as an obstacle. So we did what we call, what's really interesting is one of the researchers from Carnegie Mellon actually called Greg one day. How do you implement this downward-facing Kinect? How do you detect the plane, the ground? And then how do you tell that from obstacles on top of the plane? And she went through this, I think, a few days or weeks of development, and she came up with a solution that was very, very slow because there's so much computing required. And Greg's implementation is very fast, almost real time. So she was wondering, how do you do that? Oh, it's very simple. We didn't do any obstacle detection. We didn't do any plane detection. We just did scan line, neighbor, the difference between neighbor pixel. Okay? So all he did was run an algorithm that scanned the depth data for every pixel. So the top pixel up here, where my shoe is, up here, here. Let's say if there's a number 10. Let's say the depth information is 10, right? If the next one is 11 or 12 or anything that's less than plus or minus 5, that's not an obstacle. And keep going. Just remember what's the pixel before and the pixel after and just keep going. And what will happen is, if there's an obstacle here like this, you will see that pixel suddenly the depth become minus 10. So if the difference is so high, you just mark it as an obstacle. That's all you did. So the function is so quick, it just does a scanline scan every single time, and it merely will be able to detect an obstacle. They'll even detect recesses like this. You see this here? These are actually holes in the ground. Change between pixels, the difference between pixels. And then what you do then is, if you can look at my mouse here, once you know there is an obstacle here, you just bring it down and create an XY coordinate of where obstacles are. In this case, you see this marker here, this red band. That means there's an obstacle somewhere around this axis, and then there's an obstacle somewhere around this axis. And then we implemented a mathematical formula because the base is not square. The base is circular. So anything up here is the same distance as if it's over here. Okay? The distance from the robot is what we need. So what you're looking at here is the whole Kinect. We discount all the sides because they are somewhat error-prone from a Kinect perspective because the view is at an angle. We just look up front and we just look for obstacles. And if you see an obstacle here or here, we will turn. If the obstacle is here, we will turn at speed 10. If the obstacle is here, we turn at speed 70. The closer it gets, the faster you want it to turn. That's all we did. And we have this amazing obstacle detection, fall off the cliff algorithm that emerged from writing this simple code. I actually ran it here just now, and I was afraid that it would just run off this cliff because I can't see the difference. It's black and it's somewhat dark blue at the bottom there. But Roborazzi will see it because it's using depth profile, all right? And you'll see that there's a drop-off, starts to turn, and it avoids. So that's how you implement. And all these variables at the side here, these are all what Greg calls tweakable variables. So in his code, if you want to allow somebody to tweak those variables like speed or how fast you turn if you see an obstacle, you just mark it as a tweakable variable in your code and you automatically populate the UI. This is his sandbox. The reason it is so that when you run the robot and test, you can tweak the variables up and down as the robot is moving. Okay? And that way you can surface certain interesting parameters, certain interesting values that you stay between and that you can customize your robot with. So that's the emergent behavior sandbox that Greg built. So that's the obstacle detection. Let me show you. We can also set things like Flickr. Like in our app, what we do is we can upload the pictures to Flickr, and I can, I can set a title. And every time it takes a picture, it will be uploaded to Flickr. Okay? Now, this is the main UI, and you will see on the top left-hand corner of the UI, you see a box. When somebody comes in close, and if Kinect detects a skeleton somewhat, you will have this bounding box. And what we want to do here is that's your target area. If the Roborazzi sees a skeleton coming close, it will try and turn so that that box is above whatever skeleton. And then when it's there, I'm just going to slowly sneak in. Slowly sneak in. I'm just simulating it to turn because I'll run it around so you can see it, but I just want you to look at it. So once somebody comes into the picture, let me take a picture. Okay? So, all right, maybe that's a little bit too, to have my face up on the screen is just too much. But the code is simple, right? Can you picture it in your mind now, how simple it is when we write this code? One is move until you see an obstacle and avoid it, apply some smoothing, and you're done. Second is if the forward-facing Kinect sees somebody, find that person, tell that person you're going to take a picture, and then take a picture. Now, the say cheese was also implemented post. When we first built this robot, all it does is just turn and then take a picture. And we realized that some folks will be looking at it and like, what's happening? And the flash suddenly goes off. And very quickly they learn, but we needed to give some feedback. And we tell users, hey, say cheese, or stay still, take a picture, right? And another thing that was interesting, we started without using the flash. And then nobody knew the robot that was around. And that's also something really interesting. Everybody here is so acceptable to the fact that robots are around us. Do you realize when a robot comes behind you or up to you, nobody goes, oh my gosh, that's a robot. Nobody does that. Everybody's like, oh, cool, robot. But we don't have one at home. Nobody has one. Nobody's used to living with one, but why are you guys so, so accepted of the fact that there's a robot around, which is pretty interesting, we found out as well. So what we did was we turned on the flash, and every time a flash goes off, everybody goes, what was that? Right? And then they turn around and they find this thing really curious and they walk around it. So that's what it does. Let me just switch back to... So some of the interesting things that happened when we built this robot was kids are so clever, okay? They can trick it. Now, the Kinect has a view distance of about 80 centimeters, With near mode, I think you can drop to 40 centimeters. But at 80 centimeters, you can never take pictures like that. No way. Because if you're that close, that's practically here, like that. If you're that close, the Kinect is not going to be able to see you. It will try and turn, which is what it did at Maker Faire and any other event. When the kids crowd around it, it will start turning around and try to get away. And we were like standing back there, and we just want to, kick the kids away. But we just stood there and said, okay, patience, let's see what happens. And after a while, the kids realized that you need to step back a little bit. Okay? Step back a little bit, it triggers, it says cheese, and there's 1 second period before it takes a picture, they rush in. Like that. Okay, and that's how you get pictures like that. And that. Which was, again, something very interesting. So if we were to write code, we actually wanted to implement something where if you're so close, it would say, please step back. But we didn't. If we did that, then none of the kids would have figured out how to do this. Okay, so these are things that you learn by actually having to implement or use this in a human environment. I think you guys know, you build apps, you build web-based apps, you build phone apps, Windows 8 apps. If you think that an app is good and you build it and you think this is perfect and you let somebody else use it, oh my gosh, what a rude awakening, right? They'll go, why did you do it this way? I prefer the buttons to be up here, I want it to be there, and so forth. So, same concept, you just have to try it all the time. More so in a robot that is interactive with a mechanical software device. It's even more so from that perspective. And another thing I wanted to talk to you about, this was really funny. This was in TechEd. You were there. We had a party, an event called TechEd, which is a Microsoft event, a technical event for all the technical field staff to come into Redmond twice a year, and we tell them all the cool stuff that we're building, get them all excited. And the party was in CenturyLink Field, which is the football field, the American football field. Okay? And what we did was we ran this robot, a bunch of people will come, and then they will take pictures, smile, oh, cool, very cool. And then all of a sudden, this one guy walked up to this, and that's the guy on top. He was this visionary because he stood there, and as the device was about to take a picture, he raised his hand, thinking that that would trigger it. Okay? And indeed, it took a picture because it already saw him anyway, and he wanted to take a picture, but in that split second, he raised his hand. Everybody around him saw that. And they did it for the next 15 minutes. Everybody was around, went up to the robot, like that. And then he took a picture, obviously, because I didn't really care, right? Whether you raise your hand or not. But for the next 15, until the whole group dissipated, when the next group came that didn't see that effect, didn't realize that doing that does nothing. Which is, again, pretty interesting, right? Now, would you do that? After deciding, you see an effect like that, would you want to program so that you take the picture when you raise your hand? Not really. Why? Why would you want to wait until somebody raises their hand? Nobody likes to have the picture taken like that. Right? Nobody wants that. Everyone's like, like that. So that was pretty funny. It's not an influence graph, but I wanted to show you the kind of interesting effects that happen by having robots interact with people. So the other thing that I get called all the time, I know some of you have asked me this question as well. I walk around with this controller, and I follow Roborazzi. Now, Roborazzi is a device you unleash, you don't control. You unleash, and you hope that it will do fine, correct? In this case, of all the 8 events that it has been, and the thousands of photographs it has taken, it has only been almost knocked over twice. One by myself, and one by our corporate VP, Brad Smith, of finance. So what happened was, he just came behind, he didn't know the robot was there, he backed up, and he knocked it. That's all. But most of the time, it's very good at navigating around people and moving and avoiding obstacles. But I follow Roborazzi wherever he goes. The reason is, he might get stuck somewhere. It's another funny story. I was at an event, I let this robot run around, taking pictures. I was talking to somebody, very energetically describing, and the next thing I know, it was half an hour. I turned around, the robot is nowhere to be seen. So, oh my gosh, where did it go? Okay, well, I have faith that it will not kill anybody, okay? But it must have gone somewhere. So I went looking, and guess where it went? To the ladies' toilet. The door was open. Now, the first thing is, hey, why would you open the door? We'll leave the door open, the ladies' toilet, come on. But the robot wandered in with a camera. I was like, oh my gosh. So I was torn between, maybe I can sell the photos, or I need to go and save it. And I had to go and save it. I got somebody to excuse me, can you please just turn off the robot and then help me carry it back out again. That was pretty funny. So that's why I follow it all the time. And I'm always far away, I'll see it. If it gets stuck, I'll try and override the navigation. So with the Xbox controller, again, we learned that we just can't unleash it on its own. We need to be able to sometimes tweak it a little bit in order to give the sense of amazing intelligence, right? Sometimes we just need to trigger. Like, for instance, there was a scene where 3 kids were trying to get it to take a photo. And they were really close, and they're all hugging each other, and you would have made for a perfect shot. But they were just moving back and forth, and the Roborazzi just kept moving back and forth. Okay? And I could see the frustration in their face. So what I did was I stopped it manually, I triggered a picture manually, and then they all erupted, and then they walked away. They felt really good after that. I felt good too, but then he was cheating a little bit, right? But it was great. And that was one of the pictures with the 3 girls on the top right, okay, if you remember that picture. It was amazing so having this capability was also very useful for me. Another thing was having to drive the robot from one end of the building to another at the speed that we allow it to go to would take ages. So we also built the functionality where we can increase the speed, turn off the Kinect so it doesn't see anything in front of it, although the obstacles detection is still on, and then drive it. So you will drive as fast as you can to another site, and then we just turn on the autonomous mode again. Okay? So we built all these capabilities into Roborazzi as well. And most of the time, did you control it? When they see me holding this controller, are you controlling? I say, no, look. I'll just hold it up and let the robot take pictures. It's hard to explain sometimes. And the reason is, if you see somebody control this robot, the magic is gone. Right? It's like, that's somebody controlling it. It's not a robot anymore. And more often than not, I don't know, maybe some of you did this, but when you see a robot walking and taking picture, and then you immediately look around, like, where's the guy? Right? Where's the guy controlling it? But in actual fact, it is autonomous, right? It's an autonomous device. So I showed you the demo. I thought about showing you code, but you guys, the code is so simple here that you can just replicate the thing yourself. And you guys are much better developers than I, so don't show code, right? But if you want to take a look at code, I can sit down with you, explain to you, and show you the code if you want to, how we implemented the obstacle detection. It's such a simple algorithm. Okay, so this is my contact information. Are we? If you have any questions, send me a mail. Lokwe@microsoft.com. I'm on Twitter as well, and Facebook, Orkut, all kinds of social media sites. If you need anything. So I'm just going to let it run and then show you how I use Roborazzi. I'm going to disconnect the screen. Is there anything else? Oh, before it rips. Okay. Don't fall off. Ooh, look at that. I'm not controlling it. Ooh. 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 Whoa. Whoa. Look at that. It's perfect. Okay, you see somebody. Like, hi. Okay, fine. I have like a couple 100 photos of myself already. So if you guys want to interact with it, I'll run it around here. You can come out and take a look at it, take pictures if you want to. And it will detect obstacles like that and turn, and then, okay, don't fall. Okay, come back. And then if I want to, I can just control it and push it. Oh, no, don't look at me. Okay, I'm going to turn off the Kinect, so now it's not going to see me at all. I can drive it around. And if you want to see turbo speed, I'll just bump up the speed. The creator, the CEO of Parallax, when he built the Eddie base, he actually took off the top base, put on a small chair, and let his small daughter sit on it and drive herself around. That was pretty interesting to see. So that's all I have for today. I hope you enjoyed my session. I know there's no code, but there's a lot of interesting things to think about when we talk about robotics. I hope you enjoyed the session, and thank you very much.